Okay, so welcome to this second video on the phosphoinositide pathway. So far what we've discussed is how the activation of the alpha subunit of either the GQ protein or G11 protein by removing the GDP bound to it and adding on a GTP molecule instead, how that is going to activate phospholipase C beta, which is an enzyme within the phospholipid bilayer of cells. Okay, and this enzyme, what it does once it's been activated, it catalyzes the catabolism of a molecule that is present within the membrane of cells. Okay, so firstly let me show you the structure of phospholipids, which are usually present in, which are the main constituent of the phospholipid bilayer, and then I'll show you how the molecule which this is going to break down is a modified version of that molecule of a phospholipid, basically. So, all phospholipids are based on the molecule glycerol. So you start off with the molecule glycerol, which is basically carbon, three carbon atoms bonded together with three hydroxyl groups and one hydroxyl group coming off each of the carbons. So you have a propane molecule effectively with hydroxyl groups off each of the carbons. So the chemical name for glycerol is propane 1,2,3 triol. So this is propane 1,2,3 triol. Okay, right. So to turn this glycerol, or this propane 1,2,3 triol, into a phospholipid, what you have to do is you have to esterify two of these hydroxyl groups. You have to take long-chain carboxylic acids, which are basically carboxylic acids with a very, very long chain in this R group. So a lot of carbon atoms basically here. So for instance, if you have the carboxylic acid palmitic acid. So palmitic acid is an example of a long chain carboxylic acid, palmitic acid. And I think it might be double, well, I don't know if that spelling's right or not, but palmitic acid. And palmitic acid basically is the carboxylic acid which has 16 carbons. And all of these carbons are saturated basically. So off each carbon you have, every carbon has the maximal number of hydrogens it possibly could. So basically the structure of palmitic acid looks like so. You have the carboxyl group here, and then you have a methylene group, which you have 14 times, basically. So you have the methylene group 14 times, and then you'll have a methyl group right at the end. So that overall now will have 16 carbons, 1, 2, and then the 14 in the middle. That makes 16. So palmitic acid is an example of a really long chain carboxylic acid. Now, the old name for long-chain carboxylic acids was free fatty acids, and you'll still hear that a lot. So long-chain carboxylic acid will also be referred to as a fatty acid, carboxylic acid. Okay, so a fatty acid is the other name for a long-chain carboxylic acid. And basically what you do is you take these long-chain carboxylic acids and you esterify them with these hydroxyl groups on the glycerol molecule, and you do this for two of the hydroxyl groups on your glycerol molecule. So that gives you a diacyl glycerol. So let me show you what the structure of a diacyl glycerol is. So we still have our glycerol molecule here, but now to two of these hydroxyl groups, what you have done is you have esterified them with long-chain carboxylic acids, which basically means you attach this carboxylic acid group here, and then it's got its R group back there. So you take off this hydroxyl group here, you take off a hydrogen off this hydroxyl group, and you bind this carbon to that oxygen to create this ester link. And then you do the same here. You create an ester link with another carboxylic acid. So I put R prime there to denote that the R group of this carboxylic acid, the second carboxylic acid, may not be the same as the R group of that carboxylic acid. Okay, so you then bind hydrogens to each of these carbons, like so. Now, if I'll show you a phospholipid separately. So this at the moment, where you have bound two carboxylic acids in by ester links to the two hydroxyl groups on this glycerol molecule, that's known as a diacylglycerol, or a diacylglyceride, which is often also abbreviated to DAG. So if you ever see anyone use that acronym, what that means is diacylglyceride. Okay, so next, how do you take a diacylglyceride and turn it into a phospholipid, which is what is in it's the main constituent of the phospholipid bilayer. Well, basically, you take this, and to this first hydroxyl group, you bind a phosphate group. So, if this is the rest of the diacylglyceride, what you now do is to this hydroxyl group, and it's often drawn down here, and I don't know if I'm going to have enough space, so I'll draw it off to the side here. You have a phosphorus atom rather, and then you have a phosphorus atom doubly bonded to oxygen, a hydroxyl group like so, and an O-. So let me just remind you what the basic structure of a phosphate group is. This is the structure of a phosphate group. You have phosphorus in the center with two hydroxyl groups on either side, oxygen doubly bonded to phosphorus up there, and then oxygen singly bonded down here. So this is the phosphate group. Okay, if you're going to bind this to this hydroxyl group here, what you do is you form effectively an ester link, but it's not really with a carboxylic acid. Instead, it's with this phosphate group. So you take this hydroxyl group off here, you take the hydrogen off there, and you then bond this oxygen to this phosphorus atom, which is what we've done here. And that creates you this sort of almost an ester link, but instead of being between a carboxylic acid and an alcohol group, it's between this phosphate group and an alcohol group. And then off these two, you still have the carboxylic acids, basically. So here's our carboxylic acid. Okay. So I'll just finish this structure here. Okay, so, and then you have the hydrogens here. So that now is a phospholipid. So you've got the hydrophobic tails are referred to as these bits here. So let me circle those. So these are the hydrophobic tails here, these two. And this is the polar head down here, because it's got a negative charge, so it's a polar group. So here's your polar head. So what we could do is we could draw a phospholipid like so. We could draw it with this line representing the glycerol, these two lines here representing these hydrophobic tails, and then a circle here to represent the polar head, basically. And this is a nice representative of a phospholipid. Or another name for a phospholipid is phosphatidate. So if you ever see this name phosphatidate, what it's referring to is this molecule of two long-chain carboxylic acids esterified to the two first hydroxyl groups of glycerol, and then a phosphate group linked to the third hydroxyl group. So that's phosphatidate. And another way you often see phosphatidate or a phospholipid denoted is like so, where you omit this sort of little line representing glycerol, and you just have a polar head representing this phosphate group, and these two hydrophobic tails representing the two long-chain carboxylic acids. Okay, right, so that's the usual structure of a phospholipid, and basically the structure of the cell membrane then consists of two layers of these phospholipids, and basically the hydrophobic tails interact very favorably with one another. So the outer leaflet of the phospholipid bilayer, this outer layer of phospholipids, their polar heads are oriented out towards the extracellular fluid, and the inner leaflet, the polar heads are oriented out towards the cytosol, where there is going to be polar water molecules, basically. And the hydrophobic tails, which don't interact well with water, those face each other inwards in the center of the phospholipid bilayer, basically. So that's the structure of phospholipid bilayer. Okay, so we'll continue this discussion in the next video.